Okay, we're good. All right. So in the past, we've done a lot of deep dives on random topics. So we say this is the hot GRPO paper or whatever, and then we go and we dig into the details. So one of my ideas recently was like, let's just do broad overview of like what interesting things have happened in the past year. Maybe not technical dive, maybe just kind of brush on this lab released this, this lab released that. What's the cool stuff that's going on? So I'll be pretty brief so that we have more time for the computer vision stuff, but I just wanted to like throw out some links and show some of the interesting things that are happening. Um, so one of the ones that has really got a lot of people excited is this hierarchical reasoning model. So um, there's this ARC AGI benchmark that is essentially saying, can a model look at these sort of visual puzzles and figure out how to complete it? And these models have been getting considerably better over time. So O3 and all of the new releases have been getting better and better at these things, but they're pre-trained on billions or trillions of tokens. They're billions of parameters. They're these massive models. And so this new model, this new research model has popped up called hierarchical reasoning. And they've put things together in such a way that it gets much better results with much fewer parameters. It doesn't need any pre-training. So a lot of people are very excited about this because it's in some way people think that it's like building into better reasoning without needing to just suck up the entire internet. Um, so that's one of the new kind of state-of-the-art things that a lot of people are trying to replicate right now. Yeah.
What's the basic new architecture for that? Like, what is this other reasoning architecture here?
I don't know exactly the details of it, but basically they're saying it's inspired by the brain. So they have one segment that's doing many kind of layers, and then once that converges, it has some like extra piece on top of that. So the small repetition thing can happen multiple times. One of the things that they were measuring was basically you can't just infinitely scale a transformer to 1,000 layers, and it's not getting better and better reasoning as you're doing more steps. And so this is some way of trying to make it actually exploit that in some way. So they can scale it to more layers, and it's continuing to improve as they go to. Yeah, yeah. So I don't know the full details of it, but I know that I saw a bunch of people on Twitter basically saying like if this is real, it's a big deal. So they were bragging that they only took 160 GPU hours to train this versus the massive amount that regular LLMs are pre-trained against. So potentially very exciting if it actually proves to be a good reasoning model. Um, Moving on to the next bit. So VO3, this is a video generation model. So this isn't necessarily brand new, but right now a lot of more people are getting access to it. So they kind of announced it. They showed off, look, we can generate these videos. Now it's more generally accessible. Just Gemini, you can go play with it. And the idea here is that you can do a whole bunch of things just prompting and it will make a video for you. So you basically say something like this, saying, I want a sailor on a boat, saying this, saying that. And so it can generate these whole videos for you just given short prompts. And one of the interesting things is you can condition it on images that you input. You can condition it on videos. It can also output audio. So that's one of the big innovations here. Most video models have just been purely video and then it's silent. So you don't have anything in the background. And this has been trained in such a way that it tries to sync audio with the video. So you can end up with something where like someone's actually talking and it's trying to move their mouth correctly for the audio that's being generated. So this is a very powerful model that people are excited about, and I'm sure they'll just get better and better in future generations.
Just a question. How
Yeah.
does this thing compare to Max?
Um, I'm sure it has. So they have various benchmarks. I don't know specifically in reference to other models, but yeah, this is Google DeepMind's variant. There's a lot of other models in that family. Yeah.
Yeah, another thing, is this still like a diffusion architecture? Just like
Um, I don't know the actual architecture on that one. I know a lot of them have moved away from diffusion and actually are doing some sort of token based thing where they turn the video into tokens and then they do some latent representation there. But I'm not sure. I don't know if it's even public actually. I haven't read it. Um, yeah, I don't know. Um, so another model that's popped up is this Kimi K2. So a lot of people have been excited about this one because it's particularly good at coding and agentic tasks. So this company has kind of come a little bit out of nowhere. This Kimi one has some reinforcement learning. Yeah, yeah, yeah. Um, so this Moonshot AI company has kind of come out of nowhere. They're a Chinese company. They've open sourced this massive, probably I think it's the biggest open source model that's ever been released. It's a trillion parameters mixture of experts, and one of the things that they're talking about is they have an interesting reinforcement learning stack. So a lot of people have been doing this pre-training step where they just soak up the whole internet, and then apparently they have some reinforcement learning innovation to make it learn more efficiently. So um, that's a model that I know a lot of people have started plugging into Cursor and other places. So there's a full tech report for that. Um, Moving a little bit outside of ML, so one of the things that I've been seeing pop up a bunch is all of the robotic stuff. So we've gotten much better foundational models for robot action things, and one of the interesting innovations has been this Unitree G1. So this is basically a human robot that you can buy that has all of these interesting sensors and motors and everything together. And so this is a new platform that a lot of people are playing with in order to try and do machine learning related stuff in order to perceive the world, to move blocks, to do all kinds of stuff with these robots. And they're getting increasingly cheap. So 16K is not cheap, but in the term of having a full human clone, that's much cheaper than it was. So I saw some interesting Twitter videos of some of the new robots can even change their own batteries. So they have multiple battery packs and then they go backwards into the dock and they just swap their own batteries so they can just keep going and going. Because that's one of the difficulties with these is they either have to basically be tethered and they have power all the time, or they have battery packs that only last relatively short amounts of time. Um, Another player in this space is Humanoid. So this is a UK-based company, and they're showing off. They have these new seg 7 degree of freedom arms that can move in all kinds of different ways and balance things. So there's a lot of interesting work on robotics lately. So it's difficult to keep up with all of that, but just something I wanted to throw out there. Um, so one of the big um, kind of benchmarking sites, Papers with Code. Some of you might have interacted with it. It's this website where you say, what's the best model for classification, or what's the best LLM, or what's the best something, and it had all of these different categories. So you could go there and then you click on a certain thing, and it has basically a leaderboard of the best research models, the best commercial models, everything. And so it was a good kind of central hub for everyone to post their models and see the results. But it was just kind of a like PhD student research group that really took off, and then they've kind of sunset it. And so one of the interesting things is that Hugging Face has now picked this up. So Hugging Face said this thing needs to stay around, so they partnered with them, and now they're kind of consuming Papers with Code. So now that's going to exist on Hugging Face, which I think is a good thing. I think we need those leaderboards and all of the stuff gathered up. Um, so another one of the major players in the LM space, Quen, they released a paper along with their Quen 3. So they released this new Quen 3 model, great LLM. A lot of people are using it. And they also brought about the group sequence policy optimization. So this is a new technique that plays on GRPO and is supposed to be better in a whole bunch of ways. So people are excited about this because it made this great Quen 3 model a lot of people are very interested in the GRPO stuff because you can kind of optimize on arbitrary tasks. You don't need like your whole labeled data set. So if this is a push in that direction, I think is positive for everyone to kind of learn, is this actually better, and move over to whatever the best is. Um, so DeepMind and OpenAI, they just did this IMO Math Olympiad thing. So they have these very, very difficult math problems that they give to high schoolers, and then they compete and they say, how many of these can you solve? And so DeepMind and OpenAI used models that actually were able to solve these on their own. So in previous years, they've had systems that kind of use a crutch of some of these math formula libraries, and with this, they were able to just purely solve it just with the models on their own. So very, very big progress from both of them in terms of just solving generic hard math problems and being able to reason through things. There's a little bit of controversy with this one because OpenAI actually released the result that they got a gold medal before they were supposed to, because the IMO organization wanted them to release it after a certain period so they can announce the winners. So just throwing that out there, OpenAI did a little bit of a sketchy thing releasing that before they were supposed to. Um, One of the major things that's going on right now is all of these companies are betting huge on these massive data centers. So OpenAI has their Stargate. And so this is their massive project. They're working with Oracle to make a huge data center bet. So they're trying to build out gigawatts of capacity and billions of dollars, and they're trying to get all of this stuff through as quickly as possible so that they can win the AI race in some way. So OpenAI is making big bets, Meta is making big bets. All of them are just rushing to build the biggest data centers they possibly can in order to get as much compute as they possibly can. So part of this is getting the best researchers, part of it is getting the best compute, and then a big struggle right now is getting the most power. Like that's the bottleneck, is they just don't have enough power on the grid to even uh, provide for these capacities. So lots of interesting things going on there. I wanted to drop this semi-analysis link. So this is a website that I really like. They do great research on all of this stuff. So if you want to dig in, they really go very deep on the details of how many chips, where are they building this stuff, how long is it going to take. They're betting on supply chains and all of this stuff. So if you want to look at the gory details of how all of this stuff is getting put together, semi-analysis has very good stuff on that front. Um,
Bonuses for the people.
yeah, yeah. And so they're also analyzing how much are they paying their people. There's rumors of $100 million contracts and stuff like that for some of the top researchers. So lots of money flying around in every direction. Um, so final segment of this. So I just wanted to show basically one of the things I do occasionally is I go to the top trending models on Hugging Face, and I think that this is interesting because you just get the survey of like what are people using, what's the hot thing right now. So I'll click through a few of these. So one of the ones I mentioned earlier was Quen 3. So Quen just released this new model. This is right now the top trending model. Everyone is downloading this and playing with it and saying, how good is this actually? It'll be interesting to see if it has staying power or if it's just it got released last week, so everyone's trying it out. Um, this is Quen 3 Coder. Yeah. Um, So the other one I was mentioning, Kimi K2, that got released recently. So that's one of the top trending models right now too. This one I thought was pretty interesting. So this is actually a text-to-speech model, and they're claiming that it's the state of the art now on basically emotion. So you give it some text and you tell it, read it in a scared voice, read it in a happy voice, or add a laugh, add a chuckle, do something like that, and it's able to add all of this emotion into it. So it's interesting that text to speech is actually one of the top trending models recently because it feels like we don't hear that much about them. Um, so this one, this one's an image generation one, but it's mentioning anime and waifus and furries and stuff. So it's good to know that this stuff is out there and people are making this and it's very popular, but um just showing survey of what people are working on and what people are interested in. Um yeah, yeah. Um, so I'll jump down to this one. This one is interesting. This is from ByteDance. So a lot of these large language models, they're very strong in terms of multilingual understanding. So they understand English and French and German and whatever other language. But this one is actually a relatively small model, 7B, but it was specifically optimized just for translation. So it's just trying to translate between all the different languages. The other models kind of do it just by chance because they've seen all of the data in all the different languages. But this one is claiming state of the art for these translation tasks specifically. And so you can see it's a 7B model, but it's going toe to toe with Gemini and these 400 billion parameter models. So it's kind of interesting that you're able to pack this into a much smaller model. So if you're just doing translation, this might be the way to go. Um, so yeah, I have other models in the list, but if you want to, you can go click through and see what they are. I think with that, I'll hand it off for the computer vision stuff.
But
Yeah.
Hello, everyone. Can you hear me? Can you see my screen right now? Good. So my name is Nastasia, and I want to teach you a brief tutorial on PyTorch basics. So in today's tutorial, we will cover a multi-class classification task and cross-entropy loss function. We will also learn about PyTorch dataset and data loader. Next, we will build a feed-forward network for classification in PyTorch and discuss classification metrics and experiment tracking. So let's start with a definition of multi-class classification problem. Um, in multi-class classification problem, we add our sample to a network, and network outputs probabilities for each class. In this case, the network was trained on three classes: a cat, a dog, and a horse. And for this particular input, the network outputs the probabilities of this image to be a cat as 0.7 and probability for this image to be a dog as 0.2, and a probability for this image to be a horse as 0.1. It's remember to know that neural networks never output actual labels. They always output probabilities, and these probabilities sum up to 1. In order to train neural network model, and in order to calculate the mismatch between the labels and actual predictions, the loss functions are used. And for multi-class classification problem, the cross-entropy loss is used. And the classical formula for cross-entropy is as follows. It's minus sum all over all of the classes, probability of the target class multiplied by logarithm of the prediction of the probability. Sorry, this one, the PY, is an actual class label, and the logarithm of the prediction. So let's look at the example. Let's say our target label is 0. So our image corresponds to the first class. And before putting this label to this formula, we have to one-hot encode it. So after one-hot encoding, we have to know the actual label and the number of classes. So after one-hot encoding, we can get this vector, which is the length of the number of classes. And we can see on the first position, the number 1. That means that this label corresponds to the first class. Yeah, the first class equals zeros because PyTorch counts from zeros, not from ones. And let's say we have a perfect ideal situation and our model predicts that this image is indeed from the first class. So it predicts 1 for the first class and all zeros for all other classes. And let's try to calculate the entropy. So in order to calculate the entropy, we have to multiply the label by the logarithm of the predictions. Because the logarithm 0 is undefined, we have to add to the predictions the small number. In this case, the epsilon. We can equal this epsilon to some small number. And then we sum up across all of the vectors. So let's calculate. Yeah, in the perfect case, the loss function is 0, but it's a hypothetical case. Neural network models never outputs ones and zeros for all of the real examples. So in real scenarios, we, let's say, have label 1, and we again one-hot encode it. So for label 1 and 3 classes, we get this vector. This vector corresponds to a second example because here label 1 corresponds to a second class. And we calculate, and we have this vector for predictions, and the machine learning model is only 60% sure that this particular image corresponds to a second class, and machine learning model 25% sure that this image corresponds to the third class, and 15% sure that this image corresponds to the first class. Let's calculate the entropy of the, let's say, more realistic example. And we can see that right now the entropy is not 0 anymore, even though if we run this vector on argmax function, so we take the maximum value out of this vector, we get a correct prediction, which will be the second class. But still, the loss function will output 0.5 because this prediction, we want our model to be like more sure in the second class. So in real world scenario, yes, yeah.
This multi-classification model is specialized in classifying animals. Is that its specialization?
It's right now just a model. It doesn't really, I mean, it's true for all of them. It depends on your task.
Okay.
Right now.
So
yeah.
It doesn't specialize on one specific thing. It's just specifically for multi-classification.
In this example, we classify animals, but in general, we can classify whatever we'll train our model on. And because we had like 3 animals, like cat, dog, and a horse, so we have 3 classes. And like right now, we want to classify cats, but maybe tomorrow we will want to classify something different. Yeah. So in real world scenario, we won't write anything by hand except just the instance of the cross entropy loss function. And in PyTorch, cross entropy loss is calculated is a little bit different. Before we will discuss how it's calculated, I will introduce you to softmax. So the softmax is a function that normalizes logits to probabilities. Logits is the last layer of the neural network, the layer that the vector that corresponds to the predictions, but they are unnormalized. It means that if we sum up them, they will not sum up to 1. So let's introduce this vector with logits. Right now, just run a random vector, but let's imagine that this vector was the actual output of the model. Let's print this vector and let's see if this vector indeed sum ups to 1. No, it doesn't. And this is the softmax function that we exponentiate all of these numbers one by one, and then divide all of these numbers by the sum of exponentiated values, just like this formula. So if we run, yeah.
These are probabilities, right?
No, they are not. They are logits. They're just numbers that the neural network outputs on the last layer. Mhm.
If I could, and I apologize, you're gonna have to repeat for the people online because the audio is not working. They're not able to hear anything to say.
Oh my gosh.
Okay. Well, I could try. I could try unmuting, but I don't know if we'll get. Let me try unmute.
Okay.
Okay, so hopefully there's no feedback. So um, this is true in general for machine learning models, but especially for neural network models. We're going to build this neural network and it's going to make predictions, okay? It would be awfully convenient if the neural network could make predictions exactly the way that we want. So, for example, when you have your three classes, I'd like the neural network to output three numbers that sum to one. It's actually extremely difficult to teach a neural network to do that and to do it properly. So generally speaking, what we do is we build models that'll output any number between negative infinity and positive infinity. And then we apply, you could call it post-processing, to turn those numbers into the range that we want. So sometimes we want to turn that into a number between 0 and 1. In this case, we have multiple numbers and we want them to sum to 1. So a simple thing you could do is you could say, I'll just take the total, right? Anastasia, you calculated the sum, and I'll just divide the sum, each of them by the sum, and then it's guaranteed they will all add up to 1. But there's a problem if you do that, which you just pointed out, which is that some of the numbers are negative. And so they'll still add up to 1, but you'll have numbers within there that are bigger than 1 potentially, and you'll have negative numbers. So how can you take numbers between negative infinity and positive infinity and force them all to be positive and to sum up to 1? And it's not the only way, but softmax is a way to do that, because when you take e to a number, it will always be positive. Okay, and then if you divide it by the sum of all of those, now it's normalized to get to 1. So so that's the one of the some of the background as to softmax. It's not necessarily the one right and only way to do it, but it does make it very convenient because now you can build an arbitrary model that doesn't need to know anything about the range of acceptable values. It can just sort of say, high means I think it's this class, right? High means for the first number, it means I think this is a cat or whatever, right? And very low numbers means I don't think it's a cat. And it doesn't really need to know the range that you want the number.
Interesting. May I ask one?
Yeah.
So then, before you get to the soft max function, how would I know the difference in meaning between a 0.5 and minus 0.1? Does it have a meaning to it?
Yes, so exactly. So for the model, essentially what you're teaching it, bigger means I think it's this class. Smaller, which actually doesn't just mean 0, but actually more negative even, means I very much think it's not this class, okay? And ultimately, if you use a function like softmax, that's the only way in which you can interpret it. So you could say if cat is 3 and dog is 0 and horse is -1, then what are the final results after softmax? And then you can say what so it ends up being a nonlinear relationship. And so, yes, in fact, one of the things you need to learn when you're doing any machine learning problem is that you have a loss function, and technically, like, the loss is pushing it, and you asked a very good question, which is, how do I understand how hard it's pushing it, okay? And so that's why Anastasia showed an example where the prediction was 0.6, and the biggest number was actually on the correct class. But the loss wasn't zero because what the model's saying is, well, yeah, you said the right class, 0.6, but you could have said 0.7. You could have been more sure. You could have been 0.8. You could have been 0.9. And what you'll see is as you get closer and closer, then the loss gets smaller. And so at 0.99, it's actually not pushing very hard for the model to change. But even though 0.6 was the best, it's still pushing it to say you weren't that sure, and in a perfect world, you would be very sure and get everyone right. So sorry, that was a long
Thank you.
side conversation,
Thank you
but
for the
I hope
explanation.
that helps.
So I remind you, we have this vector with logits that we can't interpret in terms of probabilities and in terms of how. Oh, sorry. So we have right now the logits vector, but we cannot interpret the logits vector as probabilities. We cannot say how much the model sure that this is the correct class. So we run softmax function on this logits vector, and let's see how our results change. So now we can see that this vector is actual a vector of probabilities, and those probabilities sum up to 1, and we can find the class with highest probability. So our model thinks that the second class is the most prominent one. The second class is correct class.
For the two vectors, the prediction and the earlier, before we applied the softmax, do I map like each element to the, is it in order? Make like 0.09 maps to 0.29?
Yes, it's in order. Yeah, and exactly in the second vector, you can see that the maximum value is on the second position. So it's basically, we have the same conclusion, but here we have probabilities. And we actually need softmax. We don't need to calculate it explicitly in the neural network. It calculates automatically when the loss is calculated. So how exactly the cross entropy loss is calculated in PyTorch? The cross entropy loss in a PyTorch is just a logarithm of a softmax function we just talked about. And if we using math, we know that this equation is equal to these two terms, which this term is a probability of a correct class with a minus sign, and this is just a logarithm of summed exponentiated probabilities for all the classes.
But if we're looking at 3 classes, and I'm looking at several numbers there. So are we talking about the same problem here?
Right now, it's a toy example. In order to not, if you don't want, like, I know it's confusing, let's just get back to 3 classes.
Oh.
So now we will get 3 classes. But in general, cross entropy can be used for many classes, especially in large language model. Each word is a class. So like basically, yes. So, yeah, you have a question?
No, understand what's going on.
Good. Anyway, I will share my Colab notebook for those who wants to play with it. And let's implement this PyTorch cross entropy function by hand, similarly to what's going under the hood in PyTorch. So we first want to encode our label, because our label is just a single number for a single example. Then we use the ball function. We basically find, using this Boolean mask, we find just the probability of our correct prediction. And here we just take a logarithm of a summed exponentiated probabilities. Here my head vector contains all of the probabilities for all of the classes. So let's run it, and let's have another example with 3 classes as animals, and let's say the label relates to the first class, and machine learning model did a good job, and it predicts the first class. Let's calculate the cross entropy for this particular example. And the torch cross entropy will be 0.7 here. This is how the PyTorch calculates the cross entropy between the classes.
What is the cross entropy again?
It's here. So it's the probability with a minus sign of a correct class plus logarithm of the summed exponentiated probabilities. Yeah.
So quick comment. In particular, this is the loss function that we are using for this problem. So this is the function that's going to score how well the model did, and as we try to, we haven't really talked about it yet, but as we try to minimize that loss, it's going to push the model for better results. So whatever your loss function is, it should give you a lower number if the answers are more correct and a higher number if the answers are more wrong. Okay, and if you take 5 minutes later and you look at the example that Anastasia is showing, you will see in fact that if for the correct class it predicts say a 0.6 versus if you do a 0.8, it's actually going to get a lower loss for the better prediction. In some cases, the functions that we design are backwards. And so they actually give a lower number, they give a higher number for a better answer and a lower number. So then we just stick a minus sign in front of it, and then that flips the direction. So in fact, a lot of the functions that we tend to use just by chance are backwards. And so you will actually see a lot of minus signs. And so, for example, you'll hear people talk about negative log loss. And a lot of times negative appears. And that's just because the function works in the opposite direction. And if you multiply it by -1, then that changes the direction. And so we always, by convention, we always want down. We want smaller numbers to mean better answers.
Really interpreted the cross entropy actually needs the model to reduce the loss. Is that why we have that?
Cross entropy, as Anastasia showed, is a function where you can give it your predictions and also give it the ground truth, the correct answers, and it'll output just a single number, which is like your grade, your score on the test, okay? And so basically what we want is we want a function that gives you a lower score for good answers and a higher score for bad answers. So it's not like school where 100 is better and 0 is worse. In this case, the more lower towards 0, towards negative infinity, the number is the better your answer.
Okay. X is the prediction. Is the parameter X, variable X, is that the prediction?
Yeah. We just got a comment that, yeah, this Y hat, it's not predictions because we put them to the softmax. So they are called logits. This is the output of the final linear layer in a classification problem. So it's called logits.
All right, and then I think you have a question, a raised hand online.
Thanks, Ted. So,
How to accept the question?
Is the volume turned up on your computer?
All right, let me.
I'm not sure.
I don't have. I have my volume turned down. So,
are you able to hear me?
Yeah. You can whatever you want to ask a question. You can ask a question now.
Great.
All right,
Thank
go
you.
ahead, Tim.
Thank you, Anastasia. Can you scroll up
You hear
just
him?
like a little bit?
No, I don't.
Oh, you cannot hear me?
Oh, there he is.
All right. So, can you scroll up just a little bit to this cross entropy formula, the loss function formula? Yeah, that's one. So, can you kind of like go a little bit more? Because like what my understanding is like, say, if we predicted wrong, or the model predict wrong, then we have higher loss function. And if we predict it correctly, then the loss function is going to be smaller, right? The result of the value of loss. So can you kind of like explain how the prediction influence the result of the loss function when it's predicting correct and predict wrong?
So this is the logic for correct prediction. And if the model thinks incorrectly, so it outputs very small number, very small logit for the correct class. This and the small number is probably less than 0. And then we have again the minus here, so it will be the big number. So the cross entropy loss will be big just with respect to this term. And of course, we have to calculate this term, but I think this is the intuition.
Yeah, so I hope I don't get echo on your. So to recap, we have three numbers we're talking about here. There's the raw predictions from the model. Then we convert those with softmax to probabilities, right? So small numbers between 0 and 1 that add up to 1. And then the third thing we have is the output of the loss function, which is no longer a vector, it's just a single number, okay? So we do walk through sort of three steps. The raw predictions are between negative infinity and positive infinity. The softmax, as Anastasia explained, will then scale these nicely, so they're probabilities. And then now we're talking about the loss function. So in this case, the loss will always be a negative number. Okay, this is not true for all loss functions, okay? But for this loss function, it'll always be a negative number. So that means that a very small in magnitude, like negative 0.001, is the biggest number you can possibly have. And the worst number you can have is, that's the worst number you can have. And then like negative infinity, that's like the best possible number that you could have for this particular loss function, in theory.
Question, so once we converted it into number between 0 and 1, you have a number we can interpret as a probability. Is it a probability in the frequentist sense that if we run the experiment 100 times that
You want to take stab or do you want me?
You can.
So the question was, when you have this, when you've run it through the softmax and you've converted it to something that behaves like a probability, so they're all small positive numbers between 0 and 1 and they add up to 1. The question was, is it really a probability? Okay. And what I will say is the issue here is calibration. Okay. So by default, machine learning models that you create are never calibrated. Doesn't matter if it's a deep learning thing, a computer vision thing, or if even just as simple as logistic regression. They are not calibrated. So, for example, you might assume that if you just have, let's talk simpler, just a binary classifier, okay? Hot dog, not hot dog, okay? Then if you have 100 pictures that are, and some are more like hot dogs and some are less like hot dogs, you might assume that you would have like 10 predictions of 0.9 or higher, and 20 predictions of 0.8 or higher, and 50 predictions of 0.5 or higher. That might, if you're lucky, be what happens, but you might actually have 50 predictions between 0.98 and 0.999. And you might have 50 predictions between, 0.02 and 0.000, right? So there is no guarantee of the calibration of these numbers. And so, no, you should not treat them as probabilities. But if you want, you can do an exercise of calibrating them. And then it's still a little bit dicey, but then again, assuming you started with like an equal range of more hot doggy and less hot doggy, if you didn't actually have that, then you still haven't necessarily perfectly calibrated it, but at least it's somewhat calibrated if you do that. Yeah.
Would a way to think about it be not necessarily as probabilities, but as more how confident the model is that that particular input is a specific class?
Yeah, so the question was, is it better to interpret it as confidence levels instead of probabilities? And yes, but again, the thing you need to understand is that it's an uncalibrated confidence. So you might have one model where you're like, holy cow, it said 0.7, it's a hot dog. It's super, super, I've never seen a score as high as a 0.7 before. And you might have another model that you train where it's like, I've never seen a score as low as 0.7, and that's the lowest score I've ever seen. So yeah, it's a relative confidence score, and you have to know what the other confidence scores are in order to really understand. Otherwise, if you just see a 0.9, you really don't know if it's high or low.
Even at normalization, you don't know whether it's
No. If you do normalization, most people never do normalization. It's not a common thing. But if you do normalization, that helps, but you can only normalize based on some data set. And so we rarely have really good data sets for normalizing, for calibrating. Okay, right? So like if we were doing our hot dog predictor, how many people have 100 images that uniformly vary from not hot doggy to max hot dogginess? And so unless you're calibrating it on that data set, you're not really, if I just have 100 random pictures from the grocery store, I don't know if the predictions should be, 10% of the predictions should be above 0.9. Does that make sense?
this is the training. When you train them, what images you can send?
Yeah. So oftentimes, if you're training, you have images that are very, very clearly hot dogs and images that are very clearly not hot dogs. And so then it's actually not surprising if a lot of your predictions are above 0.9 and below 0.1. And so it's not clear what kind of image would get a 0.6, right? So yes, so calibrating is hard, and that's why most people don't even bother trying. And so that's the important thing. And it is a really good question, the original question of should you think of these as probabilities, okay? And so if you see something and the prediction is 0.99 hot dog, you can't automatically, if you know nothing about the model and all you see is a 0.99, you can't say like, wow, it's really sure that's a hot dog. It's 99% sure. That is not an appropriate response until you've used the model for a while, and then you're like, oh, actually, most of the predictions, are around 0.8, so 0.99 is actually very, very sure. But until you've used the model for a while and you've seen what the spread of predictions is, you can't really know just by seeing an arbitrary number if it's high or low. Okay, yeah, we can. I'm happy to follow up after the session.
Yeah, so we were just talking about how to implement PyTorch cross-entropy by hand, and it was just an example for deeper understanding of what is going on under the hood in PyTorch module. And in real life, we don't need to implement this formula, and we work in batches, and a lot of things are done automatically for us. So what we need is just to import this NN cross entropy class and instantiate an object of this class and just put our prediction and targets to this object. And then let's do it and see if we get a different answer. No, we don't. The answer is exactly the same as in our custom function, but like in real life, we need to use just this line of code. So to briefly sum up, we just talked about the loss function, which is cross-entropy loss used for multi-class classification, and it helps model to learn and find optimal parameters. Basically loss calculates the mismatch between predictions and the target labels. Let's talk about PyTorch dataset and data loader. So the dataset class defines how the data is accessed. It does not necessarily load all the data in the memory. It just maps the location of the data to a class to be able to retrieve samples by samples using this custom get item method. And the batches, the data loader is responsible for batches. So we first have to create a dataset object, and then we create a data loader, which actually creates those batches automatically and feeds those batches to our model. So a data loader is basically a wrapper for a dataset that fetches the data in many batches, and it can also do this work in parallel. So how does it look in Torch? So we have to import Torch Vision, and because right now it's a bit confusing, but we will instantiate a trained dataset object for a MNIST dataset. A MNIST dataset is a benchmark dataset for basically learning, deep learning models, and for running relatively easy deep learning models, which is basically handwritten digits. So here we instantiate this dataset as MNIST dataset. We download it, we use it in a train mode, and we use some custom transforms. And we already can iterate through this train dataset. Let's look on the dimensions of the image and label. So the image vector, it's basically, let's say, matrix. It has the shape of number of channels, height, and width. So in this case, this image has only one channel, has height of 28 and width of 28, and a label 5. And let's look at this actual image. Indeed, this image looks like a digit 5. So
So the PyTorch is the inferential Python library, right?
what do you mean by inferential?
It's the data engineering and that's that information to the machine learning model.
It both. You can like write all of the machine learning models, I mean deep learning models in PyTorch. It's not only responsible for the data, it's also responsible for the model architecture and the model training. Although there are some other packages as PyTorch Ignite or PyTorch Lightning that will, let's say, optimize the training for you. But yeah. I hope I answered your question.
It seems to be.
We'll get to the other stuff in future weeks.
Okay.
We're just starting with the data set.
Yeah, and I want to teach you how to write a custom data set. I hope most of you know the object-oriented programming in Python. For those who don't, I recommend to maybe get a brief course on data camp or something just to have the understanding of object-oriented programming and what the classes are in Python. So here we write a custom image dataset class that we inherit from dataset class in PyTorch. And we, as usual, we start to write the class with a constructor. And this constructor, we add these parameters for our class. This annotation file is just a link to the pandas data frame that holds all annotations for the labels. So here we create attribute of this constructor class, of this, custom image dataset class, and we put this table as an attribute. And here we basically map the directory with images. So we tell our class where the images are located. And we also tell it whether we need to transform either images or either labels. Then the also pretty straightforward method is the length method that returns the number of our images in the folder. In this case, it's the length of the pandas data frame that we already loaded into the memory here. And this is the most, let's say, important method for dataset class. This method retrieves the actual example for the training. It retrieves all of the samples by its index. So here, this is the path to the image. So here we create this path by joining the image directory with the actual image name. Then here on this tab, we load the image into the memory, and we retrieve the corresponding label for this image given this image index. And here we can transform either the image or the label if needed. Usually if labels are scalars, we don't need to transform them. And as a return for this getItem method, we return an image and an actual label. So similar to what we did just here, when we iterated through the trained data set, we returned a single image and a single label. But in real life, no one trains neural network on one by one. All the training comes in batches. So for batches, we need to create an object from a data loader class. So for data loader class, we have to put as a parameter a trained data set that we just created, a batch size. In this case, we put batch size of 64. And for trained data loader, we need to shuffle all of the images. So on each epoch, the batches have different structure, different images in each batch.
Shuffle is randomly done.
Yes. It's randomly on all the epoch batches are randomly formed. The only what is consistent is the batch size. So on the epoch, some random sets of 64 images are formed. Yeah, and for test data loader, we don't need to shuffle the data for test split because we want some determinism here. And so let's try to iterate. Okay, yeah.
I was just going to make a super quick comment. So we're not going to talk about all of the capabilities, but the benefit of doing this is that all the capabilities that the data loader has, you don't have to write any of that. So you want it to do batches. What happens, for example, if you do their batch size 64 and the number of examples you have is not an exact multiple of 64? That last batch is going to be a little bit smaller, right? You don't have to write the code that handles that. It's all baked in. I don't even remember, but I think if you train on multiple GPUs, the data loader can handle that. And then certainly one of the main things is most people are using PyTorch because they're going to use a GPU. The data loader runs on the CPU, and you can have it use multiple threads so that in parallel, while stuff is computing on the GPU, it's busy loading your data and copying it from CPU. All that stuff, you don't have to write any of that code. That's the bottom line.
Yeah, and you probably can also put the data loader to GPU, I think. I'm not 100% sure, but I think it's possible.
It would be rare that your data could fit there.
Okay.
Okay, but hypothetically, I guess, yes. The main benefit people get is you have a very large data set and it's slow reading it off disk, and so you have these CPU threads that are working in the background, prefetching things from disk and copying it to GPU just in time for when it finishes the calculation and it's ready to do the next batch.
Okay, so in this cell, as promised, we will iterate through train data loader. And let's look on the shapes of our tensors. And the shapes of each tensors, you can see an extra dimension at the beginning. This extra dimension corresponds to an actual batch size, which is 64 in our case. So our trained data loader outputs pre-computed images in batches. and you don't have to do anything more. Do you have any questions on this dataset, data loader part? Or we can, I think, I don't know if there was something.
Taking that, replacement, or maybe taking, shuffle. Or we just take in random values from wall set, book, without replacing.
I think without replacement, so each batch have unique images, but we probably can control that. But I don't see the point while adding, unless we face let's say imbalanced data set problem, and we want to somehow increase the number of the less represented class. Then yeah, we can like put this class more often to the model, load this class, the images of this class more often to the model, but unless from that, usually like without replacement, so the unique images each time in each batch. Yeah, there is a particular reason for shuffle because it helps, it prevents overfitting, it helps on each epoch, it helps model to see all different sets of data. That's extremely important.
Less biased.
Yes.
Which kind of database do you use to host all of your images? So this kind of work you do.
You mean to store them or? Oh, it depends on the size of the images. I mean, for this particular example, you can just store them locally. They are super small, like 28 by 28. Those images, they're like super small. They're for learning purposes.
Just simple. You're going to use a specific database to use them.
I think,
You don't need to.
yeah, for this data set, you don't need, no. So, okay, the next part, I want to introduce you to how to actually create a network using NN model syntax. So it will be similar to what we did in trained dataset. So we will need again to write a custom class that will inherit from NN module. And we will use these parameters. We'll add those parameters to the constructor and create those attributes of the class from those parameters. And we will also add some more other attributes of this class. So the first one is flatten and linear layer, ReLU activation function, and the actual final linear layer. So, and here, this is the forward method that is extremely important for, and it's used in all PyTorch neural network models. This method is actually tells the model to take the data, which is X, and to make some operations on this data. So what we do here first, so we had this vector X, which is in size of batch size, number of channels, height and width. And the first operation that we do on this vector is we flatten this vector. So instead of having this size, this vector will have this size. So everything else is flattened except the batch size. Usually it's not the case how to work with images. Usually we use convolutional neural networks, but here is just a toy example. So let's just follow. And especially when you write some new architecture, it's very useful just to have those comments in order to not be confused with all the dimensionalities and all of the operations. So after we flatten the vector, we add those vector, which is an image, to our first linear layer. And after the linear operation, our last dimension will be different. It will be equal to the hidden dimension that we added as a parameter here and as an attribute here. This is the output dimension after the linear operation. So linear operation is basically we have our vector, we multiply it by a matrix, and because the number of rows in the matrix depends on the number of columns in the matrix, in the first matrix. Here we don't the number of rows, number of columns. So the number of columns could be different. It could be whatever we want. So in other words, it could be explained as the number of neurons in the layer. I think it's more intuitive explanation. I hope I won't confuse everyone.
If I could make a quick comment, not to actually try to explain this, but this practical computer vision series, there's two like very extreme sort of schools of thought in terms of teaching things, right? So one is you learn all the fundamentals and then you build on them or whatever. And then this is actually at the other end of the spectrum, which is it's a hands-on series where they want you to have some positive reinforcement from being able to play with things. Then after a while, the stuff will make more sense because they haven't actually explained things yet. So as we're following, this is the first workshop, the one that Ryan covered last time, was how to store images into a data representation, right? And so just talking about multidimensional, storage in a tensor, multidimensional array. And this is the lesson that comes immediately after it. So like we clearly have not started building up fundamentals, okay? And so it's fine for you guys to ask Anastasia questions, but also know that intentionally the idea is that there's the Anastasia created her own notebook. There's the notebook in the repo that's associated with this learning series, and the idea is for you to play it and play with it, get a sense for it, and then we're going to ultimately start drilling down into more of the basics. Yeah, I'll link to it on our GitHub repo. The other thing that I'll say, since we are starting the ML fundamentals series, that hands-on machine learning will talk about these things that we've talked about in terms of like how do you do classification and loss functions. And so if these things are interesting to you, this is where, again, we're hoping to really like fill in the gaps in a lot of the stuff that people are talking about. So yes, so to a certain extent, by design, this is supposed to be a little bit of let me see this, and I won't understand everything, but at least it'll work, and I can play with it, and then eventually we'll fill in the details.
Yeah. All right, sorry.
Oh, that's okay. I think it's just a good start to start learning maybe how to write classes, and maybe just, I don't know, start with maybe writing a custom image dataset class. You can find very nice tutorial there, and then maybe start creating some simple neural networks that it indeed could, like, you could look at it and be scared, but don't be scared. It's like it comes with the time and with some effort. And so here we were talking that we first flatten the vector, then we multiply our matrix, with the size of batch size, and the input dimension, which is basically a multiplication of number of channels, height and width, and then we multiply a matrix to a matrix of the images, batched images, and then we got a matrix in this size, the batch size and hidden dimension, the dimension that we want to get after this linear layer. And because the combination of linear transformations is an actual linear transformation, this is what we know from linear algebra, we really need to add some non-linearity. And then we add ReLU function after the first linear layer. And after the ReLU function, we have a final classification layer that outputs a matrix in this size. Basically, for each batch, we have a row with number of classes. So each, let's say, row, it corresponds to a sample, and for each sample, the number of columns corresponds to number of classes. And this is how we actually can create a model object from our custom class. We put as an input dimension the height and the width multiplied, and we want the hidden dimension to be this number, and we have 10 classes because the MNIST data set contains digits from 0 to 9, and that's it. Maybe if you want, you can try to train this simple model and have a training loop from a PyTorch, but we won't cover it right now. I want to talk about optimizer and metrics, and hope we can still have time for that. So the optimizer. I will talk only briefly about that because there is a dedicated chapter in the hands-on machine learning, and I can see a raised hand. You have a question? Oh, okay. So the first neural network were trained with a stochastic gradient descent of vanilla SGD, which is an optimization algorithm used to update weights and minimize loss function in the direction of the negative gradient. So here in this equation, you can see the theta t plus 1 as a new parameters for the model that are equal to the previous parameters in the previous time step. Minus the learning rate multiplied by a gradient of the loss function with respect to each of the parameter. So we can represent the learning procedure, let's say, loss curve as some surface with hills and holes, and all this optimization algorithm SGD could be represented as having a ball on top of a hill and just rolling this ball down the hill in the direction of the steepest descent. So that's why it's called a gradient descent, because we want to find a minimum of this function, and we do it iteratively, one by one. So with SGD, it was a problem that the loss function could be represented as, let's say, different surfaces. So the surface could have a steep decline in one part, in one region, let's say, and it could be almost flat in the region near the local or global minima. And that's why the concept of the momentum was introduced. So the momentum is similar to the concept of the momentum in physics. So momentum basically tells us that even we reach the plateau, we still have some accumulated momentum and accumulated gradients in this case. So those accumulated gradients help us to update our weights more, like, let's say, so the update of weights depends not only on the gradients, on the, let's say, the slope on the surface, but also on all other previous gradients. And there is also another optimization algorithm that is called root mean squared propagation. And intuition for this optimization algorithm is as follows. Sometimes the loss function, the surface of the loss function could be very different. So for one parameters, there could be different, like big gradients, and for different parameters, there could be small gradients. And then because gradients vary widely, we want this could make our training unstable. And the RMS prop scales down big updates and scales up small updates. And the most popular optimizer to date is Adam, and it's a combination of a momentum and RMS probe. And this is what I will tell you for now. And if you're interested more, I recommend you to check this video and to write a dedicated chapter in the hands-on machine learning book. And yeah, I will also show how to initialize the optimizer for training. So the Adam can be imported from Torch Optim, and we initialize the optimizer adding model parameters and learning rate. And then in a training loop, after we calculate the loss, and then the loss backward means we calculate the gradients according to the computational graph. Next, we write this line, which is optimizer step. So optimizer step, it basically corresponds to updating the parameters of the model.
Sorry,
Uh-huh.
can you just, I got lost. What are we optimizing for?
I want to find a minimum of loss function.
Okay, so basically reduce it even more than what it is right
Yeah.
now. Okay.
Gradient descent.
Can you just say that?
She said something about gradient descent, so that's what I thought. Okay, okay.
We keep taking small steps towards lower loss, and we hope that we find a good local mean. There's no guarantee it's the global.
Okay, okay. Oh,
And again, we're kind of at the deep end of the pool, and we will cover all of these concepts in more detail later.
No. So
I definitely appreciate the being thrown inside the middle.
and I want also to cover briefly some metrics used for classification and experiment tracking. What metrics telling us? They are telling us how good the model is. And our model outputs probabilities. And if it's a binary classification, then those probabilities are, the model outputs a probability between 0 and 1. And to get a real class, we need somehow binarize those probabilities. So the default threshold is 0.5, and just applying 0.5 threshold, we can find that zeros are everything that is less than 0.5, and ones are everything that is equal or larger than 0.5. And then you can see a confusion matrix that will just show you how many examples are classified as positives and they were actual positives, like round truth positives, and same on the main diagonal, how many of them are true negatives. And this upper right corner shows us how many examples were predicted as negatives while being actual positives. And in this left lower corner, we can see that how many of examples are actual negatives, but they were predicted as positives. And in publications and for multi-class classification, this fusion matrix may look a little bit different. And here on each row, on each column, you can see the names of the classes. And here again, the true positives on the main diagonal. And here, for example, the true label for acne and the samples that were actually predicted as acne, there are 159 examples. And for this, the second, for these two examples, the true label is acne, but they were predicted as, let's say, psoriasis, some random research about skin disease classification. So if we get back to the binary classification, then we choose, we use the sigmund function to output probability as a like classifier, in this case, classifier layer. And again, for this binary classification, we can change our thresholds. Usually our models are not ideal, so even for default threshold, we can see some of the examples were classified as negatives and some of them classified as positives. And let's imagine we want to find the classifier that catches all the positives examples. So we want to get rid of those false negatives. Right now, it's they, for no reason, normalize this axis from -1 to 1. In real life, it's 0 and 1, and here the default threshold is 0.5. And if we want to get rid of those false negatives, so we want to be able to find all true positives examples, then we can lower down the threshold, and all of those labels, all of those samples, sorry, will be classified as positives. But at the same time, while we move in the threshold, it will also introduce much more false positives.
Is this as a result of the optimization process?
No, it's about the choosing threshold for binary classification problem. In binary classifier, the last layer is a sigmoid function, and that outputs probabilities between 0 and 1. And we want to get, again, from those probabilities, from those numbers between 0 and 1 to actual labels to know that we want actual 0 and 1s, not 0.5 or 0.2 or 0.3, and model actual outputs 0.3, 0.5, 0.7. So to binarize those outputs, we introduce a threshold. The default threshold is 0.5. So if like we have 0.3, then it's 0. It relates to 0 class. And if it's like 0.7, then it relates to the first class, the class number 1.
But it seems like
Yeah.
So similar to our earlier conversation about how the numbers are not well calibrated, okay, you don't know, is 0.8 a really high number or a low number? Okay. You don't know where the middle is either. Okay. So when we talk about choosing this threshold, so again, if I had my hot dog predictor, okay, well, what is your goal? If you say it's very, very expensive for me, because I'm trying to find all the hot dogs, and it's very, very expensive to send somebody out to go and inspect the hot dog. Okay, so then I want every time the model says it's a hot dog, I want to be quite sure that it's right. Then you might set a fairly high threshold, in which case you're going to miss some of the real hot dogs, but at least if it's costing me $1,000 to send somebody to go look at the hot dog, I know that I'm not wasting my $1,000 on having them, right? But perhaps in a different scenario, you have a very different goal, okay? And you're somebody who you're in an organization where people do not eat hot dogs. Okay. And so basically, you want to scour the kitchen and you want to make sure you throw away any hot dogs that somebody accidentally brought into the kitchen. Okay. And it's very, very important to you to get rid of all the hot dogs. Well, then you might set your threshold very low at the risk that you threw away something that wasn't actually a hot dog. But if somebody has like an allergy and they're potentially going to die if they eat the hot dog, then you say, but it's more important. It's okay to waste a little food. It's more important to just make sure I get all of the hot dogs. Okay. So that's this business of setting your threshold.
is this what we're talking about with the binary thing she was talking about?
Yeah, and there's an application of it for multi-class as well, but it's a lot simpler to talk about when it's just binary, like hot dog, not hot dog. Okay.
Yeah, so here we don't tune the model or something, we just decide how we interpret those probabilities and how we binarize them. So if we want to make a tool that detects the breast cancer, then we lower our threshold and let let the model capture all of the positive scenarios, even though sacrificing by that the model will predict some also more false positives, but at least we will capture all the true positives. So
Can I give another quick?
yeah.
So, sorry, we're already over time, but
Uh-huh.
an interesting example for me is I don't know if you guys are familiar, but there was this medical test for prostate cancer called the PSA. And ultimately, the people that decide these things, the American Medical Association or whatever, they basically recommended uh, stop performing the test altogether because they couldn't find a good threshold. The problem they had was there was a high cost potentially for false positives. Okay, if the test said you might have cancer, and then they tested people, so then some people basically had their prostate removed when they didn't actually have cancer. Okay, and that has some negative lifestyle outcomes or whatever. Okay, But if they set the threshold the other way, then some people actually had cancer, but the test said no, and then they died. And both of these outcomes had such strong negative outcomes, there was no way to give a single good recommendation to doctors. And so ultimately what they said is, doctors, you just have to talk to patients. And so, like, my doctor said basically, hey, you have to decide, is the risk of potentially worrying and having a biopsy and possibly having your prostate removed, is that risk, even if you don't actually have cancer, does that risk going to make you not want this test? On the flip side, is this small risk that you actually have prostate cancer going to cause you to have trouble sleeping at night? And so you, as a patient, have to decide which one of these possible bad outcomes you care more about, and then decide, do you want the test or not? But I can't actually just pick a single threshold that I'm comfortable with. So where Anastasia shows in the diagram, false positives, false negatives, rarely in life do you get a model that's so good that you don't have either of those. So you're going to have some of those, and then in some cases, you just simply can say, oh, I know that, whatever. In my example of hot dogs, I'm okay throwing away a little bit of food. If throwing a little food costs me $20, right? Somebody having an allergic reaction is much, much worse. So I will set my threshold very far the other way.
Because I'm working in a study machine about the constant action,
Mhm.
I would say that for the false positive and false negative, we usually go to the matrices.
Comment?
So making the balance between the specificity and sensitivity, especially for those critical models.
Can you guys hear me?
Want to make the balance. That not one of them is
Uh-oh.
going to
Can't hear me, can you?
cancer, that the recall is very important for us. But still, specificity is also important because the healthy person can go to
Hear me
the
now?
operating room without any reason, and that causes, especially for some very rare diseases like brain cancer, it may cause the same problem as false negative. So that's the reason that there are multiple matrices. Like one of them is advanced, but there are multiple that we use it and even develop it in matrices to make a balance between these.
Yeah.
So not to say that this is a threshold. No, we cannot say that this is a threshold. Yes.
Yeah, thanks for sharing. Yeah, so in medicine with cancer detection, it's difficult. I think the important takeaway lesson from this is that you cannot. So we talked about, you have three things. You have the raw predictions, then you scale those to be probabilities, and then you have a loss function. Now we're talking about a fourth thing, which is these metrics, and life is not so simple that there's just one metric that works for everything. That's the big takeaway, okay? And so you may not remember, and I don't know if we'll have time to really kind of go through everything, but Faye mentions sensitivity, specificity. We often talk about precision recall. Even if you don't remember the details of those specific measures and what they are, just understand that unfortunately, life is not super simple, and we might talk about trying to use one number as the most important number, but one number will never be a perfect picture because, again, you have false positives and false negatives as a trade-off, and unless you're just super lucky that we have a model that's crazy good and it has almost none of either, then the big picture is a little bit more nuanced.
Yeah,
All right,
and
sorry.
there were a person who wanted to ask a question. Kurt, you can speak now.
Okay, excellent. Yeah, we actually have the same situation where we automatically generate treatments and we get the same kind of confusion matrix. But what we do is we use a red, yellow, green system where red goes all the way up to the first false negative. Yellow goes from the first false negative to the last false positive. And then green is everything beyond the last false positive. And so anything in yellow gets reviewed, but the red and green go right through.
Yeah, and you hope, you hope that the yellow's really skinny, right?
Yeah, and then what happens is you work on your false negatives, false positives over time and figure out why it's doing poorly. And yeah, you end up narrowing the yellow area as much as you can. Yeah. Cool.
Okay. Last but not least, I want to talk briefly about metrics used for classification. And this one I'm pretty sure you all know, which is accuracy. And accuracy is a ratio of number of correct predictions to a total number of predictions. However, accuracy could be really, really terrible in case of imbalanced data set when we have only, let's say, 8 positives and 200 negatives. And if we calculate then if we have, let's say, a dummy model that predicts all of the samples as negatives, majority class, then the predicted um, the predicted samples will be 200 divided by 208, and we will get a 96.2% accuracy, which is extremely confusing. That's why that's a bad idea to use only accuracy to track the performance of classification model. And I suggest, and not, not me, actually, the machine learning researchers suggest to use these three metrics. The first one is called precision, and it answers the question, which is, of all the instances the model predicted as positives, how many were actually correct? So we divide the true positives to true positives plus false positives. And we have also, a recall, which is a ratio of true positives to sum of true positives and false negatives. So out of actual positive instances, how many did the model correctly identify? So those false negatives are actually gone to positives. And there is a trade-off between precision and recall, and the best metric, let's say, is an F1 score, which is a harmonic mean of precision and recall, and this is the formula for it. And I hope it's clear. Last but not least, I will say about checkpointing. The checkpointing is that we can save the model during the training. The model with the lowest validation loss or with the highest validation metrics or the highest, let's say, validation accuracy or whatever metric we use to track the progress of training. And that is used here. So if our accuracy is higher than the best validation accuracy track, then we just save the model waits in a PTH file, and then we can load the model weights for this particular model architecture and just use this model for inference. Last but not least, if you're excited about machine learning the same as I am, you can try create a training loop for Mini's dataset, because we actually wrote a model and we wrote a dataset and data loader. And then what is next is actual a training loop, and see if and how the training and validation losses will decrease with time. And I found a nice tutorial about datasets and data loaders, and you can also look at it, and thank you for your attention.
All right, thanks, Anastasia. So again, this computer vision series is the kind that starts kind of with the big picture and then kind of works its way down. So thank you, Anastasia. So this was a collection of topics. It's a little bit here and there, whatever, because it's like the basic things that you would need in order to have a running example, okay? So next what's going to happen is we're going to learn a little bit more details about some of the building blocks in computer vision, and then he's going to go into specific examples. Here's a classification problem. Here's one that's doing depth perception. Here's one doing different computer vision tasks, okay? Ultimately, it's still going to go pretty fast, all right? So conveniently, for those of you who prefer a little bit more, we do have the hands-on machine learning, which is going to start with more like tabular traditional machine learning stuff, but it will get into some of the computer vision and the deep learning stuff as we go. So If you have follow-up questions, obviously, like, the purpose we're here is for discussion, but also if you go to the book club repo, the slides, the YouTube videos that go with the series, you can also hear things a second time, and you can kind of look at it a little bit in more depth. But again, know that this was purposefully designed to show you a bunch of stuff very quickly, because the hope is that, okay, now at the end of this week and starting next week, you will have actual Python code that you'll be able to run and play with and get a feel for these computer vision tasks without saying, oh, we're going to spend 8-10 weeks on theory before we actually get to anything fun. Okay, so that's the philosophy behind this series. And so so this was officially workshop 3 of the practical computer vision series. Next month we'll do workshop 4. And on Slack, I'll post some of the details again because it's a little bit scattered. Here are the YouTube videos that go with it, here's the slides that go with it, and here's the Jupyter notebooks that go with it. All right, thanks again, Anastasia. All right, so this wraps up our session for today. Next week, we're going to have the kickoff for the new hands-on, well, the book's not new, but the new series, hands-on machine learning. I don't have the exact date. There's a holiday, Labor Day, so I think it's going to end up being September 6th or something like that is the first Saturday in September. That's when we'll have the next computer vision. And then thank you again, Ryan, for the ML News. I thought that was a really great coverage of some of the hottest, the new things. And thanks for the links. So for people who want to go and play with, if you missed it on our Slack, Ryan posted a link to the document that has links to all the new models and the articles and Twitter posts and stuff like that. All right, so we are way over time, but for people who want to talk about the Kaggle competition, we'll stay a little bit longer. Ryan's been working on that. People have asked about whether or not there's really sort of an online option. I can leave the Zoom open, but honestly, I don't know if you will be able to follow along, if you'll be able, especially without the audio video, I don't know if you'll be able to hear what people are saying. So apologize. We are only sort of promising for the Kaggle discussions to be able to work for in person. All right. Thanks, everyone. Look forward to seeing you next week.